Right, we should be streaming now. Let's see how many people will be appearing. We have 0 concurrent viewers. And then welcome to another episode of robot programming. Now I have 8 people in class. I mean, I hope I will have someone at home. Let's see if the audio is audible. The audio is audible, hence audio. All right, so the next, in this lesson, we will continue our saga with the AVR. So with the microcontroller that I suggested you to acquire. We will shortly recap the slides, especially for what was concerning the exercise, and then we will continue with the, we will present the solution of the exercise, and then in the second part of the lesson, we will be introducing new peripheral of this microcontroller or the microcontrollers in general. So, no. So, last time, if I'm not wrong, we introduced, no, I'm not wrong, we introduced the generics of how computer works, in particular how they interface with memory. We had made a small digression on microcontrollers. In particular, we figured out what are the different stages that are required for uploading a program to the microcontroller. That goes from compilation, that means we have to write our source code in some language, even the assembly if you want, and then produce some binary that can be digested by the microcontroller itself. We require a device to upload the microcontrollers if this device is the software to the microcontroller if this device is not integrated in the board, as in the case of the Arduino board. And then we need a special utility that talks with this device or with this piece of software, which is called bootloader, for converting, taking our binary that is existing on our machine and uploading it into the memory or into the flash memory of the microcontroller, right? We have investigated the AVR, and we have discovered how to set up a build chain for the AVR. In particular, the build chain or the build tools that I've given you through this makefile support also C++, while the old revision for those that did operating system were supporting only C. Okay. In particular, when we want to upload a program to the AVR, besides compiling it with the appropriate toolchain, we need to convert it to an X file that can be then digested by the microcontroller. Also, I've introduced you this simplistic makefile, and also we have edited it and seen how we can compile the things without too much struggle, just like by changing some lines into it. We furthermore introduced some basic concept. The printf today we will go more in detail, like which allows us to write data on the serial line that then we can monitor with the serial monitor to figure out what the machine was writing. And we were stressing the aspect of the digital ports. In particular, I've given you 2 examples, one for the LED blinking, which is an example on how to configure a port as output. Oh, a mosquito! How to configure them. It censored me. I mean, it's November. Those at home. Yeah, but I'm sure I will be bit. So like, I should just give up and stay zen. In particular, we have seen a LED blinking example, which was an example on how to configure a port as output, and we have seen how to read a pin. And then I proposed you 2 exercises that were only using the digital port and the like as input in particular, and they were writing something on the screen. These two exercises were one, the shaft encoder, where basically we had to monitor 2 pins of an input port, and then increment or decrement a counter based on the state machine. So this was trivially done by configuring a port as input, choosing 2 pins as input, and then entering in some sort of loop, and each time comparing the value of these 2 pins with the value of these 2 pins that we had before in order to implement the appropriate transition, right? So to go to a plus or to go to a minus. Okay? Some of you might have asked what is the state machine? The state machine is the state machine to decode the encoders. When you have a 2-phase encoder attached on a robot, basically what you have is that you have 2 light emitters and then 2 light receivers. And then when the shaft of the encoder goes from the left to the right, so let's say one ray and the other ray, right? Now, if something goes in between this ray, then you register a 0. If nothing is in between this ray, then you register a 1. Okay? Agreed? Now, what happens if you have an object that moves from left to right? Then you will see 1, 0, so 0, 0, so 1, 1, because there's nothing in front. Then the object comes from left to right. So then you start observing the first obstruction, and then you have 0, 1. Then the object passes entirely and obstructs these 2 channels, and then you have a 1, 1, a 0, 0. And then the object starts moving away, so it will move away from the back part of the thing. So you read 1, 0, and then you read 1, 1 again. Okay? So, and then this is basically encoded by the state machine. So by monitoring the condition of 2 pins before and after, you can decide whether this object was passing from the left to the right, and whether this object, or whether this object was passing from the right to the left. In addition, each passage of the object offers you 4 transitions, because you can immediately tell. So you have 4 times the resolution, because once you can capture 4 classes of events. And so you can enhance or get the maximum from the data that you have, right? So at first, I'm going to present the solution of this exercise that you might have found already, if I'm not wrong. Or did I upload it? I don't know. We'll discover immediately. Exercises, git status. No, I uploaded it. RP09. The first was a shaft encoder exercise. No. So, shaft encoder exercise. No, 06. That was a mistake. Emacs. The program, I've written it in C, but could be straightforward in C++. That nothing changes because C and C++ are basically one contained in the other, despite some little difference that you have to do for specifying the linker aspects. What is this splendid beep? It's you? Can you break your computer so that it never pings? Thank you. All right. Okay, how I have implemented this exercise is quite straightforward. Let's go to the main immediately. Remember that the exercise was requiring that we were monitoring that we were printing some output. Otherwise, how could we see if it works? And so we need to initialize the printf. And so we have to call printf init. To call this printf init, well, you have to include this file over here, right? That was the first thing we needed to do. Then the second thing is that we have to choose 2 pins on a port. I think I've selected port A, which should be the pins from 46 to 53 on Arduino, I think, or from 22 to 24. I never remember, so I have to look it up. Arduino mega pin mapping. Fantastic. And then you see, okay, Yes. Then we have to look for port A. Port A, yes. Port A is the digital pin from 23 to 29. Those from, sorry, 22 to 29. This is port A, okay? Like how do you see PA0, PA1, PA2, okay? But you could select any port that you want. It's not, I've just picked up A because A sounds like the first letter of the alphabet and it was sounding meaningful. Okay, of course, the port you choose will have an effect on the pins that you will have on the machine. Then, where was the mask? Then we have to, on which pins will we be working? We will be working on the two low pins, so bits or pins. So on the pin 0 and the pin 1. The pin 0 and the pin 1 corresponds to the binary number, so the mask consisting that takes the binary number that has the last two digits at 1 and all other digits at 0 is the binary number 3. Because 0, 0, 0, 1, 1, 0, 1, 1, and makes 3, right? So we just declare a mask that it's the bits that we want to stimulate that consists of the hexadecimal number 0x3. Why hexadecimal? Because when working with masks, it's convenient to work with hexadecimal because 4 bits of hexadecimal correspond exactly, so 1 digit of hexadecimal corresponds exactly to 4 bits of a binary number. And so we can map easily all the numbers between 0 and F to the bit configuration between 0 and 15. Okay? So the 0x means this number is an hexadecimal, which in case of 3, it's exactly the same as the decimal number 3. Okay? Very good. Then I need to configure my port for reading the stuff, and so I will have to say that the pins are for input. And to set these pins as for input, as input, I mean, I could also be, I could also be more brutal, and I could simply say I want to set the entire port as input, because who knows, who cares? But I could simply do 0xFF. But you never know when you program a microcontroller whether other pins of a port are in use by some other piece of program. So it's always convenient to do something like a selective pin thing. And in order to clear only the 2 bits that correspond to the last 2 digits, you'll have to do this operation over here. So what you do technically is that you take the mask that contains 2 bits, the last 2 digits at 1. You negate the mask. With this tilde, you negate the mask. So you have a mask that has all the bits at 1 except the last 2, which are at 0. Okay? And so you have basically the inverse mask. And then in order to clear only the 2 bits that are in position 0, you do a bit by bit AND operation between the value which was already contained in the port A and the value of the negated mask. And this basically clears the last 2 bits, but leaves all other bits unattended, because if 1 bit, which was not of the last 2, was at 0, the result of the AND between 1 and 0 is 0, so it stays the same, is the bit. If the bit was 1, then the result of the AND between 1 and 1 is 1. So basically this preserves the status of the existing digits in the port, right? And then remember that in order to calculate a transition, we need to, the transition is this +1 or -1, right? In order to calculate a transition, we need to know the value of the pins before and the values of the pin after, okay? So we need to have a variable that remembers how were the pin like in order, because, okay, I can reach the state 0, 1, either from the state 1, 1 or from the state 1, 0. If I reach it from 1, 1, then I have to say to decrement the counter. If I reach it from 0, 0, I have to increment the counter. Okay? All right. So said, kind of straightforward. We can enter our, so this thing here, previous value and current value, we could also put them here just like for cleanliness. More. All right, another operation that we would like to do is to set the pull-up resistors of the last bins, the last 2 bits of the port to 1, in a way that if nothing is connected to these pins and we perform a read operation, we're going to read a 1. In this way, we can basically toggle the switch just by grounding the pin, and we do not have to have a floating wire that we move from VCC and ground, otherwise we would read, we don't know what we would read, because the pin will be floating. Okay? If it's connected to nothing and you don't give it an initial value, you don't know what you're going to read. You're going to read what the mosquito, which is biting me, suggests in this moment. Okay? Clear? Very good. Now, in our while loop, what we will have to do, we will have to get the value of the port, pin A, and then we would have to take the current value, which is the value of the port. We would have to take the previous value, and then based on these two, we would have to perform the transition. Okay? Now, there are many ways of implementing this. The one way that basically many of you would come out would be implementing it with a gigantic switch case. No? If my state is this and the next state is this, then move this, or a concatenation of if, right? Which is the standard way of implementing state machine. Okay? Now, I don't like it because it involves a lot of if and a lot of branching in the code first. Second, if you're going to implement this in VH, so like on a real architecture, it requires a lot of if. And if is bad, because in order to, you have to say, oh, if this state is this, then do this, if. And then you have to do a lot of instructions to basically decide on which state you have to perform the transition. So like they implement, but it works, no? And that would solve the exercise. Is that clear? What we could do instead is to construct a lookup table, because if we carefully look at this state machine, we figure out that the transition is entirely indexed by the 2 starting bits and the 2 leading bits, right? So I could have actually 8 transitions, or I could have a lookup table was indexed, which contains was indexed by the string composed by the starting state and the leading state. Is that clear? So if I take these 2 bits, and I take these 2 bits, and I put them together, how many bits I have? 2 plus 2, I have 4 bits, right? How many numbers can I index with 4 bits? From 0 to 15, so I can index 16 numbers, right? So just by creating a lookup table that says +1, -1, or 0 in correspondence of an index which is consisting by the chaining of the 2 previous and current bits, I could decide whether to go forward or backward. Clearly, I will have 8 numbers which are not used in this state, in this lookup table, because I cannot have a transition between 0, 0, and 1. I live with that, right? Error, I could return a special value which is -96, which denotes an error, but I don't do it, and I just say, okay, if I skip a count, I skip a count. Okay? Now, how would this lookup table look like? It's exactly like that. In correspondence, it's a transition table consisting of integer at 8 bits, because I'm mean with the memory. And it's static because it's a global variable, and it's also const because it's a lookup table, it never changes, right? Now, the first bit, so if I move from the state 0, 0 to the state 0, 0, how much do I have to change my counter? Well, this means that the encoder didn't move, because, and so like the state has to be the same. Agreed? If the state moves from 0, 0 to 0, 1, what do I have to do? Let me look at my lookup table. From 0, 0 to 0, 1, I have to increment it. So I write a 1. If it goes from 0, 0 to 1, 0, what do I have to do? From 0, 0 to 1, 0, I have to write a -1. Right? So basically, I constructed this funny transition table. Therefore, I could simply, well, this is horrendous. Sorry. Much better. All right. So I have so each time I look at the program, it becomes always smaller, smaller, smaller. Anyway, we read the bits from the pin. We construct the index, and this is another funny bitwise operation that basically consists in take the previous value, or we could also take the previous value, and basta, I would say. Take the current value, which mask. Okay. Well, at each for loop, what we do? We extract from the port the current value. We said it's the last 2 bits. So we read from the port pin A, and then we do a bitwise end operation by considering only the 2 bits. So basically, we cleared the bits between 2 to 7, and we have only the 2 lower bits, right? And then saving operations. Delete, 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 delete. Much nicer. All right. Now, in order to construct the mask, how could we do? We have our starting state, which is the previous value, or we have our leading state, which is the current value, or I might have flipped. In one case, the encoder will count in one direction. In the other case, it will count in the other direction. So I have these 2 bit blocks, which are 2 numbers consisting of 2 bits. I need to put them together into a string of 4 bits. What do? I take the previous value, which is the bits, the first 2 bits. I take the current value, which are the other 2 bits. I take the current value and I shift it by 2. So in this way, the 2 bits that were in position 0 and 1 take position 3 and 2. We do a left shift, and then we do a bitwise OR operation. In this way, we have basically packed the 2 bits together into a number. Then we use this number as an index. It was a mosquito, or you had a question? It was a mosquito. Because I have students that together, like me, I mean, yeah, probably it's fed with me, and now it's coming to all right. Then, after this fantastic action, what we will be doing is to increment or decrement a counter, so summing up the value of the transition table. And then we spin into this loop. We print a lot of mondezza on the screen, and then we are happy, right? Now, how to test it? I will upload this program onto the board. Well, first, let's see the make file. The make file. I did it. It's like. Another one, that's a brother. Second one. All right. All right, let me delete the things. Okay, this is our makefile. We need to generate a program encoder.elf, because the original program was called encoder.c. So, encoder.elf. We could also call it encoder.cpp. It would be the same. Let's convert this program to a C++ program. File, save as, encoder.cpp. Okay? I renamed it as encoder.cpp, and then in order to be sure, I will delete the program encoder.c. Then if I issue make clean, I have strange errors. This is interesting because we have to resolve it all together now, and I will show you why this happens. What are these errors? These are linker errors. Because, if you remember the compilation stage, so let's see first the make file. Continue. The binary is encoder.elf, which is generated by an encoder either C or CPP. Doesn't matter. The objects, the other files that the system is looking for is a file called uart.either C or CPP, which is in the directory AVR common. And also, I want to tell the system that I have headers, and the headers is uart.h. This means that if I would either touch one of these files, I will trigger a new compilation. Okay? And then I include the make file. Then just by doing make, I can compile it. The horrible thing that happened now is that I renamed the program from encode, the source file, from the extension C to the extension CPP. And then all in a sudden I get these weird errors. Hey, I undefined reference to printf init. And so, why this happens? Because unfortunately, the header files of C and the header files of CPP, when passing through the compiler, they generate different linking symbols. So in theory, like if you follow that, so this means that the C++ is a much richer language rather than C. And so the syntax of C++ is not compatible, at linker level, the symbol tables are not compatible. But how can we deal with that? Okay, I will show you how in a brutal way. You can do, you know that, where is it complaining? It's complaining at which symbol is crying. It's crying from printf init, right? That's where it's crying. I mean, you could simply say to the compiler, a printf init is included in this file, right? You could simply tell the C++ compiler that this include here has a C linkage. So you by writing extern C in brackets, you're saying whatever it's inside here has been produced by a C compiler, has been parsed, the object files generated here has been generated by a C compiler, not by a C++ compiler. When the compiler will have this object module in front, it will say, okay, now I have to, there is a function, all the functions that are declared in uart.h will be compiled with a C compiler, and therefore the symbol table that I will have to find, the symbols that I have to generate for the functions that I have are C symbols, they are not C++ symbols. And then in linking stage everything will work. And in fact it works, right? Then now let's test our program, but then this is a very dirty way on how to do things. It would be much better to include this extern C in the H file of the uart function. Because if we would do so, we would basically not need to know when we write our encoder CPP file whether that object is a C object or whether that object is a C++ object. Is that clear, guys? Is that clear? The thing? Question is like, someone sells me his library. I have just a header and object file. How can I know whether this was compiled with C++ or with C? Well, try to link it one against one and against the other and you will find it out, but it's a little bit dirty, right? A nice way to do this is to instrument the library itself. So I'm gonna now open the file avr common uart.h, and I would like to put inside this header file the extern C. Okay? This solves the problem for me when I'm compiling with C++, right? I'm happy when I'm compiling with C++. But if you compile this thing with a pure C compiler, it's gonna complain because it says, hey, I don't know extern C. What is this extern C? So what could you do? Well, in this case, what you do is to use the Preprocessor Directive. Now, you should know that when the C++ compiler compiles, it defines a symbol, which is _ C++. So we could enclose these two brackets in two guards, in two if conditions, at the preprocessor level, which are enabled only when we're compiling with the C++ compiler. No. So now, what happens? When I'm compiling with the C compiler, when I'm including this file from a C compiler, The C++ macro is not, the C++ symbol is not defined at the preprocessor level. So whatever it's in here is not considered, and also whatever it's in here is not considered. So I'm just reading printf init from this file. If I'm, in contrast, I'm compiling with the C compiler, the preprocessor of the C compiler has this macro defined, and so, of course, you don't read this, yeah? And so you will read extend C and the closing word. So in this way, when we go, let me save this art, when we go to encoder C++, we remove our extend C and we can cope with both types of compilers. Now let me see if there are questions on OBS. No, OBS has no questions. There's maybe this that has questions, which are none, so I can continue. All right. Is that clear? So in this way we have healed, and so it's a good practice that if you write a C library, in the header file you write this extend C because you pay nothing for it, you copy it and paste it, and you have it polished. Okay? Okay, now the compilation went well. We find a program which is called a file which is called encoder.elf. We would like to upload it. Now, to upload it, I have to figure out which board I have, like where is my board. The message says that the temperature of my CPU is warm. It likes it. I like it cozy. I remove it. I plug it in. The message is a program that prints the kernel errors, right? And so, or the kernel notifications. Once you do something on your devices, so you're reading on the message what is going on, and it says, "Oh, I found a fantastic thingy. Oh, you disconnected. It was me before. I found the device. I queried the device. I discovered what it is. I also have a serial number. Of course, this is a fake board, but it's perfect. And it's located in TTY ACM0. That tells me where I can run the things. So in order, if you do this, some of you might have had problems in uploading the file on their device because maybe they have the Arduino mapped sometimes on TTY USB 0 or other things, especially if you buy clones or if you have multiple ones. Or if you do some mess with your serial line, then you don't know to which port it's going to map it. And so in this way you can find it out. So to be sure, Emacs, Mac e file, if you have, I think, AVR common. So if, see, it's an AVR common MK, perfect. AVR common, AVR.mk. If something goes wrong, you can change the port here. So you go into the file into the file AVR MK, and you change this into the port dev TTI USB 0. But that shouldn't be the case because I have it mapped well. Now, to upload the program, make encoder.hex. I uploaded the file. Oh, cool. I uploaded the file. Now, presumably, I think I bought 2 fantastic wires with which I can stimulate my device and read basically the encoder. Now, in order to see something, I will have to open the serial port, qtcom. No, I don't have a way of zooming. Oh, is there a way of zooming? No, there's no way of zooming. But, yeah. Open the device. Okay. And it's periodically printing me what I've instructed. I'm sorry, guys, I don't know how to make it bigger. Or, no? Is there any way of zooming in? No? All right, I mean, you see very little strings, but these tell us what is the counter, what is the index, and whatever it is. Now, if I take these 2 wires, and I put them on ground on the one end. There are pins which are labeled GND, and then you do that. And then I never remember what were the ports. We say the PI0. PI0 is pin 23 and 24. Right, now I'm gonna stimulate the pin 23 and 24. It started counting. You see that the counter value is -1. So now I'm moving in one direction. Okay, I'm taking it off. I mean, I have to 23, 20, sorry, I mean the pins are evil. 23 and 22. Now I have to figure out where is the pin 22. Okay, it's the other one. Right? Okay. -1. Okay, apparently I haven't. But, I know it. Haha. One was not grounded. I inserted to VCC. All right. Okay, -1. Now I want to go to -2, so I have to close the other one, if I manage. -2. Now I am continuing the motion, so I'm pulling the first pin that I inserted, -3, and then I'm continuing the train past, -4. Of course, it's a little bit slow because I inserted some delay into the thing, but we can solve this with interrupts, which we will see in the second part of the lesson, where we will have fun. So I hope that this exercise is clear, because we will build on it. Like, my plan would be on next Thursday to control a motor in closed loop. Now we have the first part, because we can read the encoder. And the second part will be to issue a PWM, so a signal to the motor that moves it forward or backward with a little bit of black magic, and then we will be able to have a device that controls in real time a motor in closed loop, which means that we issue a velocity and the motor will follow that velocity through a controller. I think that all of you did a little bit of control, at least the PID controller. I think that many of you have encountered it already, but if not, that's not the focus of the exercise. The focus is to develop the box around, because then the controller is just a couple of equations that you can plug in when you require. Okay, guys? Anyway, we have the encoder. Now I could also move backward, like by doing this game in the reverse order. All right, so we can read things. Second exercise was the keyboard, if I'm not wrong, which is cooler. 5. Second exercise was the keyboard. So we want to read a keyboard matrix. Now we focus just on a keyboard of 16 keys, and we want to do it only by using 8 bits. I mean, I think that in the exercise, like in the dissertation last time, I already told you how it works. Basically, we have a string consisting of a 0 and then all other ones, which is cycling through these 8 bits. And when we have a 0 onto a row, then this means that we are enabled to read that row of keys. And how do we read it? We read it by sampling the values here on the bottom. So at the beginning, we have 0, 1, 1, 1, and then we sample these bits. And then if we read here a 0, this means that the switch was closed. If we read a 0, remember here you have 0, then this means that the switch is closed, and so on. Right? Okay, guys? And the same applies here. If we read here a 0, then blah, blah, blah. Okay? I mean, what happens if you press simultaneously 2 keys on the same row? Don't do it simply, but because then you would have 0, 1, and then you will create a short circuit here, which is not nice. Okay, so press 1 key at a time, or put a resistor here. Other option. All right. You put a resistor here, which is a little bit like, say, this is 10K. Here you can put 1K, so you have a partitioning 10 to 1, and nothing brutal happens. At most, you will have some current flowing here. Okay, guys? All right. Anyway, let's do this exercise. Oh, check. The exercise was also asking that you were monitoring periodically value of the value of every single key, and to shoot to the computer to write on the serial line only when something has happened, instead of bloating it. How do you do? Well, you preserve on a side the configuration of every single key when an event has occurred. So when something has changed, when the configuration of before is different from the configuration of now, you detect which key has been pressed or released, and you send this event to the keyboard. Right? Now, once again, let's go to the solution of this exercise. Let me commit. Do you want me to commit minus 06 shaft encoder ls? First of all, we have to remove the 07 because 07 shaft encoder exercise, because it was empty. Git. Minus r. And then we go to 06 so that I upload it, shaft encoder exercise, make client, git status, git add, so that we are sure that for those at home, if they pull the software, they have, and also for those in class, they have the things. Encoder C was deleted. Git rm encoder. I have to say, okay, git status, git commit -n encoder pp. Git push. All right. Git pull. What did I do? Oh. Many things. Git push. Git push, I say. I'm dyslexic today. It's not cooperative today. All right, so let's go to 07, anzi, git rm 07, no. 07 keyboard exercise, because 07 keyboard exercise, no, that was the good one. 07 keyboard exercise. Keyboard.c. Now, once again, this is a C file, but I will convert it in a C++ file, and I will do it with git. Git mp, okay, keyboard.c, keyboard.cpp, so that I will now be consistent with what I've taught you. And we have it here. So, now, let's design this struct key event. Okay, the very first thing that we can do is to define an event, because in the end our program has to send events over the serial line. Or, in general, an event consists of a key number that tells us which key we have pressed, a key number that goes between 0 and 16, but even if we use 7 bits, it's not dramatic. And we would like also to have a bit that tells us whether the key is pressed or released. What you see here is a synopsis of the Bitmask in C. I mean, I'm just giving you insights. If you, after a variable, you write a column and a number, this means that you are selecting the 1 bit of whatever follows. So this means, give me a bunch of bytes in memory. And the first bit of this bunch of bytes, make it accessible to me as if it was a thing that I call status. And it's let me access it as if it was an integer of 8-bit. But of course, you will only be considering the last bit. Okay? Then the second thing is, let me see the 8 bits of this bit field, the 7 bits of this 8-bit field, as another integer value, as if it was an integer of 8 bits. Of course, I will be considering only the smaller one. This is a way of packing the structures, and in this way, this key event will only occupy 8 bits. It's absolutely not necessary to do it. We could also do this and live happily, but yeah, if you want to use the memory to its limit, especially in microcontrollers, you can use these things. They are very useful, these bit structures, when you want to access the flags of a register, because you could define a register as a uint, as a struct, where the first bit corresponds to the first pin, the second bit maybe corresponds to another pin, and you can call these pins by their function. Sometimes the pins of a register have a specific name. Like in case of the uart, there will be a pin that tells you whether a character has been received or not. So in this way, instead of playing with bit masks, you can just read and write a pin direct, a bit direct. All right. Another thing that we're gonna need is a bit string that contains the configuration of every of the keys of our keyboard. And it sounds quite sensible to store this configuration into a 16-bit number, where each bit will correspond to the corresponding bit key. Great. And then we can start with our fantastic routine. But first of all, we have to define where are we gonna attach our keyboard on our hardware. And then here I see that I used the port A. So I mean, I'm fond of port A, which means that I'm gonna use the pins between 22 and 27, 22 and 29, sorry, for handling these 4+4 connections of my keyboard. Agree? Okay? And 4 of these pins will be used as output, and other pins will be used as input. How do you do that? Well, look in the main. I'm using the port A, and I'm using the 4 most significant bits as output, which will denote the rows. And I'm using the least significant bits as input, which will denote the columns. Okay? So what are the most 4 significant bits? Is a bit mask consisting by 1, 1, 1, 1, 1, 1, 1, and 0, 0, 0, 0. Which in hexadecimal makes F0. Okay? So now, in order to set, I can configure the entire port by writing in the data direction register F in the first 4 bits and and 0 in the other bits. In addition, in order to implement this circuit, I have to enable pull-up resistors on these pins over here, right? To enable pull-up resistors, which means by default read 1, I have to set to write 1 to the pins that I'm going to use as input. And I'm going to do this, going to do this here. Port A, 0x, 0f. So put up the pull-up resistors on the least 4 bits, even if you're using them as input. Okay, then we have a fantastic array of key events, whatever it is, which will contain the events, right? And we have a function that we call Keyscan that will write on this array of key events, basically, all the events that have happened, okay? Because maybe in one, you might have multiple events when you scan a keyboard. You might have 2 keys on 2 different rows pressed, even if you shouldn't be doing it, okay? Clear? Very good. Delicious. Okay, our Keyscan will work as follows. We'll start filling this array of events and we'll return you, starting from 0, and it will return you the number of events that you actually have sensed in this iteration. Okay, guys? That clear? So, if you have 2 events, you will have the first value and the second value valorized, and the number returned by the function will be 2. Okay? Now, remember that we have to shoot an event only if the new status is different from the previous status. This is the previous status, this is the new status. And this is the number of events, which obviously is 0. We use also a variable that we call key number, that it will go between 0 and 16 while we do our operations, because at the very end we're going to scan one key at a time. Then we have an outer loop that loops through the rows. How many rows we have? 4. So we have this R that goes between 0 to 4. I could also be more mean and write this, just to save even more from my microcontroller. And then what I have to do is remember what I have to do when I want to read a row. I have to put on my columns, on my row, on these bits, a string, on these bits, a string which is consisting by a 0 in the row that I want to read and 1 everywhere else, right? These bits corresponds to the 4 highest bits of port B, okay? Of port A, okay? So I need to generate a number which is 0, 1, 1, 1, 1, or 0, 1, 0, 0, 1, 0, 0, or 0, 0, 1, no, 0, 1, 1, 1, or 1, 0, 1, 1, or 1, 1, 0, 1, or 1, 1, 1, 0. These are the numbers that I want to generate. Trivially, I could obtain it by shifting a 1 and then negating the bit, as I've done with the mask before. Only I have to consider that these are the 4 most significant bits of my game. So what I am gonna do is to shift this one by instead of by a number which is added to 4. In this way, I'm gonna cover the 4 most significant bits. Okay? Is that clear? Then once I have a mask which is consisting of 0, so of 1 and all zeros, or 0, 1 and all zeros, and so on, I can negate it and then having the enabling that I want to have on my rows of the matrix. And this is the big game. Okay, then once I have generated the value that I want to read onto this column, I just write the row mask on port A. Then remember that we are dealing with electrical signals, so it's good to wait a little bit for the signal to stabilize on the port, especially if we have a weird thing. So we wait 100 milliseconds. 100 microseconds. And then otherwise we might read some clobber. And then we have to read the entire row. To read the entire row, what we do is to take the port A, the pin A register, which is the input register, and mask it in order to consider only the least 4 bits, right? Now, this is the row we read. So we are reading a bit string that has a 0 only in a correspondence of the pressed key, okay? Or in correspondence of all pressed keys, because you could also press 2 keys simultaneously on a row, okay? And so, given that we like to consider the key pressed as 1, we just negate the resulting value. So a key pressed is 1, a key released is 0, okay? This is the other operation that we do. And then here we have frozen our value. We have read it already, right? Now we can parse it, we can elaborate it in order to figure out what has changed and what has not changed. So, as a consequence, remember that we have two nested loops. One which goes between 0 and 4, and the other one that reads the column which goes between 0 and 4, right? So, what how we would like to consider in our 16-bit number the bit that corresponds to the red key. And basically, this red key is obtained by the number. So it's a bit that you take this key number, which is a variable that will be incremented in the inner loop, so it will range from 0 to 15. And then you take a 1 and you shift it in correspondence of the chosen key. And also, well, you have the column mask, which is we're gonna read the bits the bits that we have sampled one by one, right? So for each column, basically, determine which one is the key. So this is a 1 in position of the key, and determine determine the mask, so a number that contains a floating 1 in correspondence of the column that we want to read. Okay? This is something that we call it a column mask, and then how do we see if the K in the row R and the column C has been pressed? Well, we take the sampled value of the row, which will have a 1 because we negated it in correspondence of the pressed key, and we do a bitwise AND with the column mask, right? Or we could simply write this, given that we are in C++, right? This is a 1, okay? That clear? So in this way, we know if the key is pressed, okay? Clear? And, well, and then if the key has been pressed, we remember that this was our key mask. Now we are compiling, we are constructing our key mask. We have to set the corresponding bit to the mask, to the global configuration of key. Remember that the key mask is the status is a 16-bit number, and then and this key mask will contain a 1 in correspondence of the key that we are reading. And what we want to do is to update the status to reflect the fact that we have pressed the key number, the key in position pos. Okay? So we do a bitwise OR operation, and we have set the bit. Agreed? Clear? And then, as I said, we need to figure out whether something has changed or not, right? And so to figure out whether something has changed, we can simply take the previous configuration of the keyboard, the current configuration of the keyboard, and if they, even better. We can simply take the previous, this is a bool, so that I can avoid this not equal 0. And I can also delete this. Oh. Like we can consider, now what we want to figure out is whether this key was pressed in the previous iteration. To figure out whether this key was pressed in the previous iteration, we take the key status, which is our variable which was storing the status of my keyboard in the previous instant. It's a 16-bit number. And then we basically read the bit that corresponds to the key we want to get. And so this variable over here is going to be 1 if this key was pressed before, and it's going to be 0 if this key was not pressed before. That clear? So we have current select and previous select. Now, an event is generated if a key in the previous iteration was different from the key in the current iteration. So we can simply see if these two events are different, and if they are different, we are constructing an event, writing the event in my number of events, and increment the number of events. Okay? And then we remember that I told you that inside the nested loop, we advance our key number, which ranges from 0 to 15, which will be then correspond to a mask of a number of a 1 that floats into this 16-bit number from location 0 to location 15. Okay? And then we iterate the process, basically. That clear? At the end of the game, remember that I've incremented the number of events. At the end of the game, we return the number of events. And of course, we set the next key status to be the same as the current key status that we have reconstructed during our iteration. In this way, we avoid doing shooting events for keys that have not changed. And this is the main program that basically loops, runs the key events, and until the events have not been, until you didn't read all events, you printf the status of an event and a key of an event. Okay? Now, if I upload this thing on my Arduino, uploaded, and now I'm ready to test this thing. Remember that for testing this program, you will have to short circuit one of the first 4 bits of the port A with the lower 4 bits of the port A. We're not playing with the ground because in our circuit here, these are 4 bits of a port, these are 4 other bits of a port. We have no pull-ups. Okay? No? In order to, these are PA0, PA1, PA2, PA3. This is PA4, 5, 6, and 7. Okay? So what I'm going to do is to stimulate the bits corresponding to the port that I never remember. So 22, so I have to connect one pin between 22 to 25 with another pin between 26 and 29. Okay, now I'll do something wrong for sure, but let's see what's going on. I open my Qt.com, open. Now I'm pressing a key. Okay. Event 1, 0. So this means that I pressed the key number 0. Now I'm releasing the key number 0 by pulling out the wire. Event 0, 0. Now I'm pressing the key number 1. No? Wrong? Yes. No? No, this was the key number 4. Well, I mean, the numbering is a little bit dodgy. So no, probably, okay. Okay, I know it. Pressing, releasing 0. Pressing, releasing 1. Pressing, releasing 2. Pressing, releasing 3. Okay, now I've done the first 4 keys. Now, let's try the other 4 keys. Second row. Pressing, releasing 4. Pressing, releasing 5, I think, yeah. Pressing, releasing 6. Pressing, releasing 7. So, I'm testing my keyboard. Can you see a little bit, guys? Sorry, but I can't zoom that much. All right. And then this would work also with other keys. Let's try to press 2 keys and to break my Arduino. No, works. Works. But mystery of electronics. Okay, it works also simultaneously pressing 2 keys. All right, so now we have a keyboard, right? So we could do a mini computer, but we will not be doing that. All right, so this was for the exercise. Let's see if I have questions here. There are no questions at all. Just for a simple poll, these 2 lessons are a recap of what we have seen in operating system. I'm sorry, guys, but for those of you, how many operating systemers do I have here? Lift your hands. Like 1, 2, 3. No, you didn't do it. No, 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 no. Very good. So, like at least I have I hope. Are you understanding it a little bit better this round? Like that we go slower. So. What? I'm fine. You're fine. Like how can I? How can I?
No, but that's my fault. Because I've been following you, but
you haven't been doing the things.
I tried. And I didn't have the basics, so I just followed the lectures without doing the exercise problem.
Yeah, I mean,
every time I have to do an exercise, I always have to see again your lecture.
I see. But I mean, this is a problem of the course that squeezes. I mean, actually, I would need 12 credits to teach you C++ properly. But we have too many things to say, and and we have 3, right? And I think I'm already overloading the hours. I mean, thanks one goes to the university not only to pass the exam, but also to learn something. All right. But yeah, I understand. So your colleague says that, yes, a little bit of trouble, sorry, for those at home, because it requires to do the exercises, to rewatch the lesson before doing the exercises. This is almost unavoidable, and thanks God the lessons are recorded. Because sometimes I write and I type fast, but if I would have to go slow, then we would never, reach it. At least something is there, I'm sorry. Anyway. All right, then we can go to the second part of Arduino. And in case we would finish earlier today, no one would suffer, right? Do you have another lesson after me?
Yes.
Okay, so then... Shift F5. Shift F1? F5. Now, so this is, we're done with exercises, and let's do the timer, another bit of AVI. And what we will be doing is to talk about another peripherals. So far, the only peripheral that we have seen directly were the digital ports, and implicitly the serial port, but we were just using it as a debug instrument. Timers are used and are living in microcontrollers. There's a profusion of timers, and are special digital machines that they have some sort of level of smartness, and then they can be configured. It's like when you buy an alarm, you can configure it to do multiple things. A timer is, the concept of a timer is trivial. You have a register that, based on some sort of event, is every time incremented or decremented each time the event occurs, right? And it's a register, which is a variable. You access it as if it was a variable. And by reading or writing in this variable, in particular, you figure out how many events have passed, right? How many events happen. But this doesn't require the CPU to do anything. This is a device that runs on its own. Okay? So you could have a timer on a side that, for instance, counts the time. Counts the time that has passed. Right? This is the first use of a timer. And you could use it, for instance, to measure how long your CPU takes for executing a certain routine. You have this peripheral that it's running aside, and then once you enter a routine, you get the number. Once you exit the routine, you get the number, you make the difference, and then this difference is going to be the time that has passed between you enter your function and you exit your function, right? And so you have an idea on how long has passed. Agreed? This is the very first use of a timer. Very intuitive. You could also use a timer in this way, for instance, if you want to read a sonar. If you want to read a sonar device, which is this sensor that measures the distance through the echo of the ultrasound, you fire the sonar. The sonar says, oh, no, and then it starts listening, and when he hears, no, which is himself shooting back, it stops counting, right? And this way you measure the distance with the timer. Okay, an example of how to use the timer in counter mode. Another way you can use timers is that we will not necessarily see, is to use the timer in a little bit more intelligent fashion. Imagine that you want to have a mega resolution of timing. So let's say you want to have a sonar, but you don't want to poll on a pin to figure out when the sonar has been received, right? And also you don't want to write, we'll see it later, an interrupt routine that when you hear the echo stops the timer, because this will incur in the latency of the interrupt. So when the interrupt comes, it says, oh, a processor, and the processor, oh, what was I doing? Then you have to save the state of the stuff. Go to the interrupt table, read the interrupt vector, jump to the interrupt vector, start executing the interrupt routine, and already many cycles have passed. If you're interested in having a super accurate timing, you could use a timer as a peripheral that stops counting when a certain value of a pin is received. So in this other way, you have a timer in running mode, freely running mode. You configure this digital device to say, hey, monitor this pin, dude. Start counting. When this pin changes status, for instance, stop counting and send me an interrupt. So in this way, the timer freezes the time, and then in your interrupt routine with all the calm, you can go there and then read, hey, how much time has passed. This is the second way. So capturing the time at which an external event occurs. Another way you can use the timers is to generate waveforms. And this is a little bit tricky. Microcontrollers, they do not generate analog values. It's possible to generate analog values from a digital number by using a digital to analog converter. You might have seen it in electronics. You can do it, but nowadays, especially for robotics, this is not the way you generate a signal. What you typically do is that you generate a square wave, right? Square wave, 111, 0, 0, 0, 0, 1, 1, or 5 volt, 0 volt, 5 volt, 0 volt, right? And by altering the duty cycle of this square wave, which is, you consider a period of the square wave, and normally you have a period which is 50% of the time high and 50% of the time low. This is how we all imagine the square wave. But if we would have a square wave that has the up part for, I don't know, 75% of the time, and the low part for 25% of the time, then that would still be a square wave. Okay? Now, this square wave can take only two values, either 0 or 5 volts, or 0 in VCC. No? What we can change by using a timer is the duration of the period. Like the duration of both the period, which is the entire time that I go up and down and up again, and also the fraction of the time within a period that this wave stays high. Okay? So if I generate a signal that is high 75% of the time and 0 25% of the time, and if I integrate it over time, then I get a pseudo-continuous signal that it's at 75% of the value, so to say. If I want to generate a signal, so the game is that you put a low-pass filter at the exit of this PVM, and the low-pass filter will return you more or less the average value that you read into this square wave over time. Okay? And that's the way you simulate it. Plus, many devices that they don't really care, because in the end, the low-pass filter is consisting by the device itself, because the devices, the motors typically are extremely low frequency. And so if you give it a square wave with a certain duty cycle, which is the fraction of the signal that it's high, what you expect the motor to sense, it doesn't care because it has inductances and so on and so forth. It will not think that it's receiving a square wave. It will think that it's receiving a continuous signal, which has a value proportional to the fraction of the time that the duty cycle, so the high part of the period, was high. Okay? Second way. So by doing, you can generate waveforms using timers. How? You configure the timer in order to say, hey, dear timer, start counting forever. And now, once you reach this value, please toggle this pin. The timer counts when on its own. When it reaches the value that you told him it has to reach, it says, oh, sorry, pin down, and then up again. So, but this is not done by the CPU. You don't have to write a program that deals with the pin. This is done by the timer itself. Okay? And another way we can use the timer, trivially, is to attach the timer, the output of a timer, and to say, hey, dear timer, whenever you reach this number over here that I've told you, instead of toggling a pin, send me an interrupt. And this is another way you could use this same thing. And we have done this just by a thing that counts. Right? It's a very simple, so it's a very simple piece of electronics, but all this can be done by a thing that says 1, 2, 3, 4, 5, 6. Then when it reaches the end, it restarts 1, 2, 3, 4. Okay? Now, on the Mega, you have 5 timers. Some they are at 16 bits, some are at 8 bits. What does it mean, 8 bits or 16-bit? 8-bit can count up to 255, and 16-bit can count up to 2 to the 16 minus 1, because then it restarts to 0, from 0. That's the difference between the timers. The increments are attached to the clock. So a timer can count at 16 megahertz, because Arduino has a clock of 16 megahertz, which means that the counter can count, like the period could be 1 divided 16 million, the frequency of counting. However, 16 megahertz is a gazillion. How much do you take? How much does it take to finish the counter at 16 megahertz? Even a counter at 16 bits, I don't know, divide the 16 million by 16 bits, right? Roughly said, 16 is 2 to the 24, 2 to the 8, 1 divided 256, should be something like that, no? So which will be a frequency period which is higher than 100 hertz. We are in the range of 100 hertz with a 16-bit time. So what normally you have, the interesting thing of a timers is that the timers are timer 0, 1, 2, 3, 4. No, timer 0, timer 1, timer 2, timer 4. I think we have also timer 5. So actually there are 6 timers, but I don't know. You check how many timers there are in the documentation. Each timer is characterized by this most important thing, which is a register that counts. This register is accessible as a variable in C++ or in C, and it's referred to count, timer count, and x, where x is 1, 2, 3, 4, 0, 1, 2, 3, 4, whatever. Okay? And given that this value can be 16-bit as well, you have 2 registers, the lower and the upper. So if you do the lower 8 bits and the higher 8 bits. If you have a register which is 16 bits and you want to access all 16 bits as a uint16 value, then you write to count A. If you want to access only the lower 16 bits, then you write to count AL, to count 1L. If you want to access the higher 8 bits, you write to count 1 H high. Okay? Clear? So each register is associated with each timer is associated with a counter. The counter is the register that contains the numbers. You can access these. Let's say the X is a number that denotes the number of the counter of the timer that you have, right? You have up to 5, I think. I don't know. Let's see, Arduino, how many timers do I have? If just T mega timers 256 timers. No, 2560 timers. Oh, 60 datasheet. Come on, let's download once again the dataset. All datasheet. It's. Oh. I don't want to buy it. Okay. So timers. Timers. Oh. 16-bit timer. Timer 0. Timer 3, 4, 1, 3, 4, and 5. Okay, we have 5 timers. There's no timer number 2. Okay, because sometimes they like to omit a number, no? You have the timer number 0, you have the timer number 1, and then you have the timer number 4. Why? No? Just, I think for consistency with the other series of microcontrollers. No? That they have a timer 2 that is devoted to a special function. This microcontroller of the family doesn't have it, and then they want to. So we have 5 timers. That's the AVR. Now, each timer is characterized by Shift F5. No, F5, right? Each timer is characterized by a counter register, which is referred to count. And then X is a number, 1, 2, 3, no, 0, 1, one of these timers that you have that denotes the specific timer that you have. Now, the timers can be either 16 or 8 bits. Now, for timers at 16 bits, the count is 16 bits. For timers at 8 bits, the count is 8 bit. In addition, if you have a timer at 16 bits, the library defines also two additional fake registers that do not exist, which are to count high and to count low, that map to the higher and lower bits of the register. But we don't care about that, right? Because the AVR can read only 8 bits at a time, and so sometimes if you want to use pointers or stuff, you might want to access to exit bits to the exit cycle. Then, in addition, another register that you have is a control register that it's called timer compare control register or whatever it is. And then once again, you have a digit that identifies the counter. And then once again, given that it's a 16-bit register, you can go select the lower or the highest part of this register. Okay? Then also we have another thing attached to a timer, which is a register that controls the prescaling. So you don't want to run at 16 megahertz necessarily on a timer. You might like to lower a little bit the frequency at which it counts, right? In order to do that, there is a simplistic circuit that is put on top of the clock that is passed to the signal, which is called the prescaler. The prescaler is basically a device that divides the input clock by a power of 2. So you can say, okay, run this timer at 16 megahertz or at 16 megahertz divided by 2, 16 megahertz divided by 4, and so on. By changing the prescaler, you change the frequency at which the timer is updated. We will see everything in code now. In addition, each timer, now this is the big spiegone, but you will have to see the code actually. Each timer is attached to special register which are called output compare. Output compare, what is a register which contains output compare? An output compare is a number that has to contain a time, right? And you have 3 output compares attached to each timer, and each time the timer changes the value, implicitly the device compares the value of the counter with the value that you have written on an output compare. If this value is equal and you configured it appropriately, the timer might generate an event. In this way, with the same running timer, each time the timer goes on, you can generate up to 3 different events. You can say, ring the alarm when when you reach 20, ring the alarm when you reach 100, and ring the alarm when you reach 800. Okay? That's how the AVR works. Okay? It's not me that I've made it this way. Why 3? I don't know why 3. Why did they put... I don't know why it was done like that, probably for silicon considerations on how many things you want to put on a chip. Okay? So, let's wrap up the timers. We have three registers, let's say, attached to a timer. One register, which is the counter, which is incremented by itself. One register, a bunch of registers, which are the output compare, which are attached to the same counter. Okay? And what they do, then we have a prescaler, that is the thing that divides the clock. And ultimately, clearly, we have a control register that will be used to configure the different behaviors of a timer of different things. Now, I don't expect you to, let's say, study these things, because these things are made to be forgotten. You have the data sheet of the AVR. The important thing is that with this introduction, then you are able to understand, and with the examples that we will provide, you are able to understand how the things work and how you can look it up. Okay? This was the introduction to timers. Now, let's see the very first example. Now, the first example that we do is that we run a program that configures a timer in free floating mode. So, timer, just count. And then the timer will be there, will be counting as much as it wants. And then every second, let's say, we will be read this value and printing it on a serial line. Okay? This is the very first example. And so, let's see this example. Or P, no, 09 AVR, 03 timer. Emacs. All right, this is my full example. What we do, the only interesting thing that we do, is that we will use the timer 4, and in order to configure the timer 4, we want to basically reset it, because this timer 4 might be configured to raise interrupts, do whatever we want. To do so, basically, what we do is that we clear the control register, timer, counter, control register of the timer 4. A means the upper part. No? This is a 16-bit register, and we are only, no. Yeah, this is an 8-bit register, but we have multiple timer control registers. Now, let's see in the documentation. How do I read the documentation? I go here, 16-bit timer, this one over here. Okay, this is the configuration. I hope you can see it. This is how the timer circuit, one single timer, this is the circuit of one single timer. Like, you see that this is the timer, the counter of the timer. These are the 3 output compare registers. And these are the 3 control registers, that are attached to this timer. And then stuff can be used. In particular, this device here, OCR, can be used to generate the waveform. Remember the PVM. This other one can be used to generate a waveform, and so on. And additional stuff. The important bit is that in order to figure out how to configure these devices, we have to go here, or more easily Google for it, and you will find out the usage of these horrible timers. This is the counter. It's a pain. The counter, no, this is the counter. Waveform generation mode. In somewhere there will be the bits. So basically what you figure out, now I don't want to dive into the datasheet because we will lose too much time and it's not relevant. Because in the end I'm not asking you to change the bits of the AVR. What I want you to understand is simply I had to write some bits in some control register to enable that particular function. Okay? And these bits correspond to clearing the register. No, what was it here? To clear this register. Another thing that I need to do is to configure, because otherwise the timer runs at 16 megahertz, or I don't know how it runs. I have to configure the prescaler. The prescaler is the part of the chip that divides the clock. How to configure the prescaler? Well, from the documentation, you have to write down this string into the timer counter control register for B, so the second register. Let's see if we are more lucky with the datasheet with this. TCCR, so Prescaler. Let me Google for Prescaler. I have found that because before yes, I'm more, no, this is wave generation mode. Prescaler. Oh, Prescaler, yes. Very organized, this manual. Okay, now to divide it by 1028, you have to write this bit. And this CS means the number of bits. So this ranges from 0 to 8. That's how to read it. And here you find all the documentation of the single bits in the control register. This is an absurd pain. My suggestion when you work with a microcontroller, especially with the peripherals, is to look at another another project which is similar. You say, oh, this is the way to use the PVM. You take it, you massage it a bit, and then you know at least where to look in the datasheet. Because the datasheet is never organized according to your mind setting, okay? Anyway, we divide the clock by 128, and then while 1, we read the value tcnt4, because tcnt is the timer counter register of the timer number 4. Okay? We read this number and we print it. Fantastic program. It will just write numbers. Timer read. Hex. Okay. Make timer read. Did it work? Yes. Now Qtcom. Open. And as expected, it's writing the number that is counting. Okay? Now I could have fun, because if I change the prescaler to count faster or slower, then I could have a different behavior for this time. Right? Now we see that it takes a little bit to reach the saturation. It's a 16-bit number. Now let's see if I change the prescaler. How do I change the prescaler? I look in the datasheet, and I write, I don't know, now I divide it by 124, I could divide it by 256. So I have to set 100, right, to these bits. Let's see. So CSN2, N is the number of timer, right? So this will be CS42, CS41, CS40. CS42, so I just like delete this thing. And now I expect that the timer will progress much faster. Then, am I in the right shell? Yes, it's the only shell. Ah, yes. All right, let's see. Open. As you can see, it's much faster in reaching the saturation. And this is because I changed the prescaler. By changing 1 bit, now the counter progresses much faster. And my program reads only each second, right? So, okay? Now we have seen the role of the prescaler at least. How to toggle the prescaler? By setting that horrible bits into the corresponding control register of the timer. Remember that the counter is 1. Okay? Guys, I'm asking you, would it be fine for you to go on until 1:30 and then I set you free? Or would you like to have, and no, because if I leave, then you have no place where to go. No, io la stanza non la chiudo, però c'è un limite massimo. Arriva il cattivo. Sorry. Yeah. No. So then let's shift to 5. I'd say I finish with the timers. No, I continue with the timers in the next episode. I stop the streaming. I take questions from online and from the presence, and then we restart at 1:30, so that you have a place where to go, because I will be around. Let's see if there are questions, because I'm not able to look at them, but there are none. So it's fine for you? Now, if you have questions, I'm taking questions now, so that also the people at home hear. No? I mean, no questions that can be answered, well, also from home. Maybe, well, then have fun, and maybe when I switch on the business, you will be more talkative. Stop streaming.